Hi everyone, here's a video solution, I guess, of the last assignment that we did. Not only do I want to talk about the answers to this, I also want to introduce this idea of adding a new kind of vector to your motion maps, that of an acceleration vector that indicates the direction of the acceleration, which is kind of important if you're going to describe a motion. So here goes. Remember, generically, that's what we're looking at for a position function for any object that has uniform acceleration. In using this, oftentimes a lot of things cancel. So in this particular case, the object began at the origin, so no initial position, at rest, no initial velocity, but did have a positive 1 meter per second squared acceleration. So the only thing that actually remains, this first term cancels, second term cancels. Since there's no initial velocity, you're only left with this third term. So half of the acceleration would be 0.5 meters per second squared times t squared. That's your position function. The velocity function is always a little bit simpler because these are always linear, at least in this course. The initial velocity was 0. That term cancels in this case, leaving us with the acceleration times the time. If you use these two functions to determine the position and velocity at all of the times listed on the table here, this is what you get. Down here, motion map. Here's where you're going to see a new thing. The positions are indicated by these dots. Remember, position indicates where an object is. You're used to drawing these vectors to indicate the direction of motion. In other words, what way is the velocity pointing? Now, these were all positive velocities, so these were all right-facing velocity vectors. Well, a new kind of vector that you can draw on these to indicate that the thing was not only moving to the right, but also accelerating to the right, that's a positive acceleration, you can add small arrows above the dots to indicate the acceleration. So these would be acceleration vectors. You might be thinking, okay, well, why do the velocity vectors get longer and longer as time goes on, and why do the acceleration vectors all stay the same length? Well, let's look at the table here. The velocities are actually getting larger in size as time goes on. So that's why these vectors are getting longer and longer as time goes on. But the acceleration doesn't change. Every second, this thing's velocity changes by 1 meter per second. So this is a constant 1 meter per second acceleration. And so those vectors shouldn't get any longer as time goes on. Since the position function had a squared term in it, you're going to get a parabola. And the velocity and acceleration look like such. Like I said, for a constant acceleration, you're always going to get a linear velocity graph, and you're always going to get a horizontal or unchanging acceleration. All right, this new motion. Object began at rest, so implied that initial velocity is 0 and initial position is 3 meters. So this thing doesn't begin at the origin. This object began at the 3 meter mark, but still accelerates at positive 1 meters per second every second. So looking at the position function here, the first term stays. There is an initial position. The second term, there was no initial velocity, so that part canceled. The third term, half of the acceleration would be 0.5 meters per second squared times t squared. So this is what you're left with for a position function. As far as velocity goes, there was no initial velocity, only the acceleration times the time. First term canceled. So if you use those two equations to fill out the table, here's what you get. This object began at a position of 3 and moved to the right. Velocity increased over time by 1 meters per second every second, and there was the constant acceleration. So let's look down here. The motion map, here are my right or positive accelerations that are constant. Here are the right but increasing velocity vectors right there. Now you're going to notice that this motion looks virtually identical to the one on the previous page. Literally, the only difference is where the object began. So the dots are spaced the exact same way that they were here. They're just beginning at the 3-meter mark instead. Once again, this object is accelerating, so you're going to get a parabola for a position time graph. There's a squared term. But the velocity time graph and the acceleration time graph, they look identical to what they did before. There was no difference in the velocity function. Literally, the only thing that was different, the parabola here is shifted upwards 3 meters from where it was in the last motion. Third one. So this object begins at the origin, implied that x naught equals 0, but is moving initially to the right at 2 meters per second and accelerates to the right at 1 meter per second squared. So how does this pan out in the position function? Initial position, 2 meters per second. I'm sorry, initial position was 0. Initial velocity, 2 meters per second times the time, plus half of the acceleration is 0.5 meters per second squared times t squared. That's what you're left with. This first term cancels out. Velocity function. Initial velocity, v naught, 2 meters per second, plus the acceleration times the time, at. So using those equations, you should have been able to fill out the table with these values. Where the object is, how fast it's moving in what way, and how the velocity is changing. So in this case, since the object was initially in motion, I drew a velocity vector on this first position to indicate that it had a 2 meter per second velocity at that point in time, accelerating to the right. Now notice something here. This object's moving to the right and accelerating to the right. That means it's speeding up. And if you go back and look at the previous ones, this object's moving to the right and accelerating to the right. That means it's speeding up, same way it was on the first page too. I want you to kind of keep that in mind for when we get to the next motion. This object was moving to the right and accelerating to the right. If both of those are positive, that means the object is speeding up. Notice your parabola is a little bit steeper at the beginning. The previous ones where the object began with 0 initial velocity, notice the position time graph didn't have any slope to begin with. Since this object was in motion to begin with, position time graph has an initial slope. It doesn't start with a flat line basically, or a flat part of the curve. Velocity time, still sloped. In fact, the slope of this graph is 1 meter per second every second, but it does not begin at 0, begins at 2 meters per second. Still, the acceleration time graph doesn't look any different. In fact, all 3 of these so far, you've had an acceleration of 1 meter per second every second. Interesting to see that some parts of this can look the same and other parts can look different. The last couple here are a little bit more involved. Let's look at why. So this thing began at the 10 meter mark, initially moving at 2 meters per second positive to the right, but accelerates at negative 1 meter per second squared. So this is how the velocity is changing. It's changing by negative 1 meters per second every second. So what effect is that going to have on the motion here? Position function looks like this. So x naught is 10 meters, v naught is 2 meters per second times t, minus, because this was a negative 1 meter per second squared acceleration, so minus half of that, 0.5 meters per second squared times t squared. So you have a negative sign right here, should anyways. Velocity function velocity equals initial velocity plus acceleration times time. So acceleration was minus 1 meters per second squared. Forgot my squared. So if you use these equations, you're going to find that, look at the position. It begins at 10. X naught was 10 meters. It's moving to the right, so it got further away from the origin. Moving to the right still, but watch. Then it starts to get closer to the origin. So this thing began at the 10 meter mark. 4 seconds later was back at the 10 meter mark. So look at the motion map. Began at the 10 meter mark, went further away, actually turned around and started coming backwards. Now, these accelerations were a steady -1 meter per second every second. Notice, if the velocity is to the right, but the acceleration is negative to the left, that means the object is going to slow down here. The velocity was to the right, the acceleration was to the left, the object slowed down. In fact, the object was briefly at 2 seconds here, it was stopped. That's when its velocity was 0. Then, that same exact negative acceleration now means the object is speeding up, going in the negative direction. So one of the things we tried to kind of get out of your mind with one of the experiments that we did last was a negative acceleration does not necessarily mean slowing down. It can mean slowing down, but it doesn't necessarily mean slowing down. If the velocity is positive, but the acceleration is negative, that does mean slowing down. However, if the velocity is 0 or negative acceleration doesn't mean slowing down, it means speeding up. And that's kind of evident here if you look at the velocity versus time graph as well. The slope of this is a steady -1 meters per second every second. That's the acceleration, -1 meters per second every second. So at the beginning, when the thing was moving with a positive velocity, yes, that did mean the positive velocity was getting smaller and smaller and smaller. At 2 seconds, the velocity became 0. Then the thing started to move backwards to the left, speeding up at 1 meter per second every second. So this negative sign shouldn't necessarily tell you whether the thing is speeding up or slowing down. You've got to look at what way it's moving additionally. This is just how the velocity is changing. So all of the acceleration vectors should point to the left, since this is a -1 meter per second squared acceleration. And you shouldn't have acceleration vectors on your paper at this point. I'm just trying to introduce this idea to you. This shows that the object started at the 10 meter mark, went further away, slowing down, got to the 12 meter mark, and then started coming back towards the 10 meter mark, speeding up. And there's the steady -1 meter per second squared acceleration. Okay, last one. So this object begins at the 5 meter mark, moving at -2 meters per second. So even though it starts at the 5 meter mark, it's moving to the left at 2 meters per second to begin with, but is experiencing a +2 meter per second squared acceleration. So x naught, 5 meters, v naught, -2 meters per second. Half of a is +1 meter per second squared, because the acceleration was 2 this time, so half of that is 1. V naught is -2 meters per second plus acceleration times time. The table fills out like this. Check those values. Now remember, this thing began with a negative velocity, so it started moving to the left, but was experiencing a rightward acceleration, a positive acceleration. So once again, if the velocity is negative and the acceleration is positive, that actually means the thing is slowing down. So it's slowing down and then moving to the right afterwards, speeding up. So kind of like on the last one where a negative acceleration didn't necessarily mean slowing down, a positive acceleration doesn't necessarily mean speeding up. It did slow down for part of this time, but then it sped up for another part of the time. This kind of indicates that. Start at the 5-meter mark, moved to the left, got closer to the origin, slowed down, stopped briefly, turned around, started moving to the right, speeding up. Velocity time graph. Thing began with a -2 meter per second velocity. The slope of this would be the acceleration, so the slope of this should be +2. So took a second for the thing to come to rest from -2, and then began to move to the right. Ended up going 6 meters per second to the right by the end of it. And there's the constant acceleration that caused it.